As I have already mentioned, one of the purposes of group theory is to be able to say when two groups are isomorphic, so look identical from the point of view of group theory, and which aren't. So we start with the following easy observation, namely, isomorphism is a bijection. So if the two groups do not have the same number of elements, that means there couldn't possibly be a bijection between them. So, phrased in the language of group theory, if G and H are groups and their orders are not the same, remember the order of the group is the number of elements in the group. If their orders are not the same, then the groups are not isomorphic for sure. So examples, easy examples of groups that definitely look different even if you just use the lens of group theory. Z mod 4Z is not isomorphic to Z mod 5Z. Z is not isomorphic to Z mod 4Z. Because the order of Z mod 4Z is 4, the order of Z mod 5Z is 5, the order of Z is infinite, the order of Z mod 4Z is 4, so they are definitely different groups. But question, is Z mod 4Z isomorphic to Z mod 2Z cross Z mod 2Z? How many elements do you have here? 4. What about there? I can write down the elements of this group. They are 2Z, 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 1 plus 2Z, 1 plus 2Z, 2Z, and 1 plus 2Z, 1 plus 2Z, comma 1 plus 2Z, this exhausts all the possibilities, so there are also 4 elements. Oh, so both of the groups have 4 elements, right? So they must be isomorphic. Well, if that was the case, then you wouldn't really need much of group theory. This statement only works in one direction. If I have two groups that have different number of elements, they are definitely not isomorphic. But if I have two groups that have the same number of elements, they may or may not be isomorphic. So we need more tools to be able to distinguish whether two groups are isomorphic or not when they have the same number of elements. These will be tools from group theory. I'm not going to be using anything other than that. There are some tools from group theory that will allow us to distinguish between some of them. Okay, so for this, so it's question mark here, right? Is it? So we begin with some basic properties of homomorphisms. So start with something called proposition 0. And proposition 0 says the following: let G and H be groups, and phi from G to H be a homomorphism. Then phi of the identity in G is equal to the identity in H. So the identity is always mapped to the identity. And in fact, in the proof and in what follows, I will usually just drop the subscript G and H, and you are supposed to figure out which identity I mean from the context. The thing inside the parentheses must be an element of G, so when I write phi of E, that E must be the identity of G. On the other hand, this identity here is phi of something, so it's an element of H, so it would have to be the identity of H. Alright, so let's prove this. So I do the following, phi of E. So again, this is EG. That's the same as phi of EE. Here in between these two, I use the binary operation in G. So it's EG star G, EG. Okay, phi is a homomorphism, which means I can write it like this, and now this here is the multiplication, the binary operation in H. So now look at this, right? So I have this equal to that. This is an equality of elements in H. So I apply, so multiply both sides. By phi of E inverse. How do I know that phi of E has an inverse? By definition of a group, every element has an inverse, right? No, remember, this is in H. This is an element of H. Okay, so that, what do I get? So on the left, I get phi of E inverse, right? I'm multiplying both sides on the right, let's say. On the right, it actually doesn't matter where you multiply it, on the right or on the left, because the group H doesn't have to be abelian. And so I get phi of E inverse. Oh, but what is that? Any element times its inverse is the identity. Where is this equality happening? In H. So that's the identity in H. For just now, I'm just going to put this H here underneath to emphasize that I'm in H. And here the multiplication is in H is associative, so I can do this first. So that is the identity in H. So that means this is phi of E. H. But that's the same as phi of E. Because identity times anything is that anything. So what do I have? I have that this identity here is equal to that, which is what we wanted. We wanted phi of E, G, to be equal to EH. So identity is always mapped to the identity under any homomorphism. Okay. Proposition 1. Let GH be groups n be an integer. Let phi from G to H be a homomorphism. Let G, little g, be an element in G. Then phi of G to the n is equal to phi of G to the n. So, remember our notation, right? What does G to the n mean? That means I take G star G star G, so I have n G's altogether in that expression, and the multiplication, the starring, happens in the group G here. And here, I take phi of G and star it with itself, so I have n phi of G's there. And that multiplication happens in H. All right, let's try to prove that. And let me just show you. So first of all, if n is equal to 1, this is clear. Yeah, because that means just phi of G is equal to phi of G. So, duh. So now we proceed by induction. Suppose phi of G to the K is equal to phi of G to the K. We want to show phi of G to the K plus 1 is equal to phi G to the K plus 1. Okay? That's how induction works, right? I check the base case where n is 1, and then I suppose that the statement is true for n equal k, and I'm trying to show that it's true for n equal k plus 1. We have, what do we have? Phi of G to the K plus 1. Oh, right. So this is for K greater than or equal to 1. So we're only looking at positive exponents at the moment. So this is equal to phi of G to the K, G. Right? G to the K plus 1 means exactly that. Now phi is a homomorphism. So that's phi of g to the k, phi of g. Remember, this multiplication here happens in the group G. The multiplication between the phis happens in the group H. So I get that this is now my inductive hypothesis. By inductive hypothesis, I know that phi of g to the k is phi of g to the k, with k outside. Now, right, think this phi of g is just an element of h, and this is the same element of h. So it's like some element h to the k times h. That's h to the k plus 1. So we proved that phi of g, that phi of g to the n is equal to phi of g to the n for all positive n's. Okay, we still have to deal with 0 and with negative n's. If n is equal to 0, then we get what? Then we want to show phi of g to the 0 is equal to phi of g to the 0. But our convention meant that g to the 0, that's just e in g. And again, this is an element of h raised to the power 0. By our convention, that means EH. So I actually already know that. That's proposition 0. Proposition 0 showed that phi of the identity in G is equal to the identity in H. However, this is true. We already know that. By proposition 0. Okay, so that leaves us with negative n's. And to do this, I'm going to show that it's actually true for n equal minus 1. So now let n to be minus 1. Then what do I want? Want to show phi of g inverse is equal to phi of g inverse. However, one has, let's see, phi of g inverse times phi of g. Now this multiplication is in h. So that is phi of, now phi being a homomorphism, right? Phi is a homomorphism. Means I can now bring these two back inside the parentheses. But that's just the identity in G. But phi of the identity is equal to the identity by proposition 0. So what does that prove? That means that this is the inverse of that. Okay, we're using the uniqueness of inverses here. This is the inverse of that, because this times that is the identity. So phi of G inverse. Right? This is the inverse of that. This is the inverse of that, and this is the inverse of that. So this is phi of G inverse as desired. Okay, that's what we wanted. So now we know the statement for all non-negative n's and also for n equal minus 1. So now let's take an arbitrary negative n. So now let n be greater than or equal to minus 2. Okay. Then I write phi of g to the n as phi of g to the minus n inverse. Or maybe, I mean, it doesn't really matter. I'm just going to do it the other way around. Minus n inverse. Right? If you recall what g to the minus n meant, that by definition, this bit was g inverse all together n times. So when I take the inverse of such a thing, I get just g n times. So I just get that. Okay, so for once, this is equal to phi of g to the minus n inverse, and that is because we proved this equality here. Right? This is because so by the statement, so by the proposition applied to a group element g to the minus n and exponent minus 1, for which we already know the statement of the proposition. We proved the statement of the proposition is true for any group element. This is my new group element, right? Think about it as some sort of g prime. Inverse is phi of g prime inverse outside. But now what? What about phi of g to the negative n? Now the negative n, because n is less than or equal to negative 2, negative n is actually positive. So I can just apply this property. So this is equal to phi of g to the minus n to the minus 1 by the proposition for exponent greater than 0. Okay, and combining these two, again, looking at what that means, that is just right, phi of g inverse n times. If you take the inverse of that, you get that that's phi of g to the n as desired. So this finishes the proof of the proposition. Now we have it for all possible n's. Okay, and this is actually very useful when proving some of these properties that we want. So proposition 2. So let G and H be groups. And let phi from G to H be a group homomorphism. Be a homomorphism. Then let G be in G. Then you might wonder what happens if G has a certain order. How is the order of phi of G related to the order of G? It turns out that the order of phi of G is always less than or equal than the order of G. Remember, this means the order of phi of G, and this means the order of G. The order is like the smallest positive power that brings the element back to the identity. If phi is injective, then this is actually an equality. right, let's try to prove that. So, proof. So let n be the order of G. And m be the order of phi of G. So we're trying to show that m is less than or equal to n. So let's see. So I try to raise phi of G to the power n, not to the power m, but to the power n. What do I get? So by the previous proposition, I can put the n inside. This is proposition 1. I can put the n inside. Oh, but n is the order of G, which means this is the identity in G, as n is the order of G. So this gives me phi of the identity. Oh, but by proposition 0, the image of the identity is the identity in H. So what did I just do? So n is a positive integer because it's the order of G. It's the order of something, so it's always a positive integer. So phi of G to that positive integer gives me the identity. And what is the order of phi of H? Phi of H, the order of phi of H is the smallest positive power that gives me the identity. So that means because phi of G to the n gives me the identity, the order of phi of G is less than or equal than n, right? The order is the smallest one that makes it happen. N makes it happen, so the order must be less than or equal. So this proves the first claim. So now let's assume that the map is actually injective. Now suppose phi is injective. Then we have, well, we definitely know that E is phi of G to the n. Right? M is the order of phi of G. So if I raise phi of G to the m, I get the identity. And now by homomorphism, proposition 1, I know that this is phi of G to the m. Okay? So, G to the n, let's write it like this. So, I have that phi of G to the n, the m, is equal to phi of G to the n, is equal to the identity, right? How do I know that phi of G to the n is the identity? Well, look here. That applied to any map. Phi of G to the n is the identity in H. On the other hand, I also know phi of G to the m is the identity. Okay, but if phi is injective, that means different elements must be mapped to different elements. Because G to the n and G to the m both are mapped to the same element, they couldn't have been different. They must be the same element. As phi is injective, this implies that G to the n is equal to G to the n. Okay, that's true, but actually I wanted to say something different here. Also, what else maps to the identity? The identity also maps to the identity. Right? The identity in G maps to the identity. That's proposition 0. So really what I wanted to say is that therefore G to the n must be the identity. G to the m. Okay, so note, both G to the m and E are mapped to the same thing. So because phi is injective, that means they must have been the same element. So G to the m is equal to the identity. Oh, but what do I know about m and n? I already know that m is less than or equal to n. So this implies, because n is the smallest integer for which G to the n gives you the identity, so this tells me that m must be greater than or equal than m. Right? Again, n is the smallest integer whose power, such that G to the n gives me the identity. Because G to the m also gives me the identity, that means m must be at least as big as n. So I have now these two inequalities. So m is equal to n. Let me just quickly recap this, okay? So we had this inequality for every function phi. Now suppose that phi is injective. Then we have that E is equal to phi of G to the m, because m is the order of phi of G. So phi of G to the m is the identity. By using proposition 1, I can put the m inside. So that means phi of G to the m is the identity. Yeah, this is sort of irrelevant. Phi of G to the m is the identity. But on the other hand, what else is equal to the identity? Phi of the identity. That's just proposition 0. Phi of identity is mapped to identity. So I have two elements, G to the m and the identity, that are mapped to the identity. Because phi is injective, different elements map to different elements. So if these two guys are mapped to the same element, they must be the same element. So E must be equal to G to the m. But what does that mean in terms of orders? The order of G is n, which means n is the smallest positive integer such that G to that integer is the identity. But because G to the m is also the identity, that means m must be bigger or equal than n, because n is the smallest possible. So you get the inequality in this direction. So now you have both inequalities. So you get that m is equal to n. M was the order of phi of G, n was the order of G. So we have proven now this equality.